So in this circuit that we're given, we see we have these terminals A and B. And so they're asking us to find the Thevenin equivalent for the circuit outside of that. So that's this part of the circuit here. And then they want us to use that Thevenin equivalent that we find to calculate what the current would be through this RL. So the current flowing through there. So let's go about and see what this is going to entail. So first, let's think about what we're solving here. So we're going to take this resistor out of the equation for now, because we're just trying to find the equivalent Thevenin circuit between these two nodes here. So the first thing we can do is we can calculate the Thevenin resistance. And so that's if you were to put a meter between these 2 points here, ohm meter, what would you expect to measure? And so the way that we can do that is we can just reduce the resistive network between those two nodes. And remember, we short out voltage sources and we open circuit current sources. So in this case, we only have the one voltage source here, so we can short that out as shown here. And so now we could redraw this then to make it a little easier to see what we're doing. So we have this leg here in red, and so that's 1,000 ohms. So we could just write a 1,000 ohm resistor there. And then we have this leg here in blue, which is 250. So let's go back and say this is 1,000. And then we have the next one right here, which is, actually, let's draw that in blue since I was using blue. So the next one here, which is 250. And then we have our original A and B here. So we're looking into this to find out what this R-Thevenin is. And so it should be pretty obvious there that R-Thevenin is going to be 1,000 ohms in parallel with 250 ohms, or that's 1,000 times 250 over 1,000 plus 250. And when we calculate that out, that comes out to 200 ohms. So that's our R-Thevenin. So we'll put that in our back pocket, and then we come back here again with this being gone. Now we want to think about what the voltage difference between A and B is. That'll be our open circuit voltage. So we'll call that our VOC. And that's going from A to B. So to do that, though, we're going to define this current that's traveling around this this loop. We'll just call that I for now. And so we can determine what I is just from Ohm's law, and that's voltage over resistance. And so in this case, the only voltage we have is 60 volts. And then the resistances, we have 400 all in series plus 600 plus 250. And so when we calculate that out, that comes to 0.048 amps. So now our voltage from A to B, so that's going from, let's clean this up a little bit. So then that's going from, again, get rid of this, from A to B. So that means we're going to travel from here to this point. What voltages do we see? Well, we've got the voltage in this 600 ohm resistor here, And so we can write that then. That's going to be 600 ohms times the current, which we just calculated here, 0.048. And then we're going to have the next resistor, this 400 ohm resistor. And so we can write that one and as 400, again, times the same current goes through them, 8. And so then that's going to be 1,000 times 0.048, which that comes out to 48 volts. And so this is our open circuit voltage. So now we have our Thevenin resistance and our open circuit voltage. That should be all we need to do this circuit. So remember, when we do a Thevenin equivalent circuit, it's a voltage source, which in this case, that's going to be 48 volts in series with a resistance, which in this case is 200 ohms. And so we can go back to our original terminals A and B. And now if we look back at our original circuit, see that we're putting a, we'll do this in red, we're putting this 40 ohm resistor across A and B. And so this is 40. And they've asked us to calculate what this current is flowing through here. This current right here. So we'll call that IL. So now this is just an Ohm's law problem. So we can calculate IL. So IL then is just voltage over resistance. So in this case, it'll be 48 over 200 plus 40, or 48 over 240. And that comes to 0.2 amps. And so this is the amount of current that should be flowing through the 40 ohm resistor, 0.2 amps. So that's the current flowing through here, 0.2 amps. And that was used solving Thevenin's equivalent.